Hey robot makers, hope you're having a good day so far. So do you want to learn how to build your own wall drawing robot? Then this is the show for you. So let's dive straight in. My name's Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, let me get over to the slides and we can make a start. So yes, this is all about a wall drawing robot that I've constructed in my robot lab just over here. And we'll talk about why and what it can do. So what exactly is this? So over the past couple of weeks we've been creating a few different types of drawing robot, and I thought it's about time that I took one of the ideas off my ideas list and actually started working on it. So to my right I have a great big, it's about 1 meter by half a meter roughly, whiteboard, and I usually put on 3 months so I can quickly glance over and see the calendar, and I can circle any events and count down to or count up to events and so on. And I've always thought it'd be really great if I could have a robot that would draw that, or draw anything on there in fact. I have to sort of lean awkwardly over the desk and draw it, in my handwriting is not great anyway. So I've had this as an idea for quite some time. So I want to build a wall drawing robot, one of these kind of gondola style ones where there's a little pen in the middle suspended by 2 cables with 2 servo stepper motors either side. That's what I want to do, and I want it to be able to draw the calendar itself. So that's the kind of goal where we're getting to. It's probably going to be at least a 2-part video, this one, because there's quite a few different things we need to cover off. So let's talk about how to build this robot. So electronics wise, there's quite a few different pieces of electronics that we need to use on this project. So I'm going to use a Raspberry Pi 02W. This is a Raspberry Pi 02W. This one hasn't got the header pins on yet, but that's what I'm going to be using. There are other slightly older Raspberry Pi 2Ws that you could potentially use. We're just running Python on this, so it doesn't need to be too powerful, to be honest. Next we need a couple of stepper motors. So I'm going to be using these 28 BYJ48 stepper motors. So they've got this quite small form factor. They're not the style that you normally see in the 3D printers. They're the NEMA 17. This is much more compact and smaller, and it's just got the cable on it there. And that usually comes provided with a stepper motor driver, which is this one here. I'm just going to go the right way around. So this is the ULN 2003 stepper motor driver. So you can see there it's got the nice big white plug. It's got a couple of interesting LEDs on the right hand side. We'll have a look what that's for. There's 2 cable header pins for 5 to 12 volts, and on the left hand side there is 4 pins which we can use to drive the actual individual magnets inside the motor to make it step round. We need a bunch of DuPont cables because we're going to be wiring things together, and we also need some of these, which is the teethed gear. So it's got 20 teeth on it. I think this is a 3GT 8mm timing cog. It's got these 2 little black grub screws in it, and basically we can just attach that in there and just screw it on so that we've got a nice pulley system going on. And that also means we need to have some pulley cable. Not sure what you actually call this timing cable. It comes like on a really neat spool like that, and it ends up just being like a big mess of cable that's like 10 meters long or something. And of course we will need, it's not electronics this, but we'll also need some kind of marker pen. I've gone for these Beryl dry white pens. These are the ones I've been using on my board. So I've been using the diameter of that, which is about 18 millimeters, as a guide. So then we need some 3D printed parts. So we need some way of attaching these stepper motors to the whiteboard itself. So what I decided to do was create 2 pieces which can attach to the whiteboard board. I'll show you exactly how we do that shortly. And these have got all the right kind of measurements and holes to put all the screws in and so on. And the left hand side one has also got an extra space for the Raspberry Pi Zero to sit, so it's got all the right measurements. I was using my Robot Maker's Almanac to get the exact measurements I needed for the Raspberry Pi Zero. I think that's in there somewhere. Flips through. Anyway, yes, I've been using that, and they'll be going on sale. Honestly, promised. Been promising since January. We've got the shipping sorted out, so that should be a matter of just pressing the button on that. The middle 3D printed piece is what we call the gondola. That's going to hold the pen. It's also going to hold... That was a very loud ding. It's also going to... thought I'd muted that. Let me just mute my... there we go. Do not disturb until tomorrow. There we go. Sorry about that. Yes, so the gondola, it basically houses the pen. It houses a little servo motor that can push the gondola away from the drawing surface so that the pen removes and isn't touching and therefore doesn't make any marks. And we can control that sort of pen up, pen down. And it's also got a couple of slots for the timing cable to go into and be screwed into place. On the right hand side, it's simply just the other stepper motor and the stepper motor driver board. So that's the three pieces that we need to make this all work. So assembling this together, quite straightforward really. So the Raspberry Pi Zero, all Raspberry Pis have mounting screw holes which are M2.5. I don't know why they chose 2.5. It's the size that you never get when you buy like a box of screws on Amazon. They always have like, you know, M2, M3. So you have to specifically buy M2.5, or you can just grind through with an M3 screw if you really want to do that. The driver board, that seemed to take M3 screws quite fine, and the stepper motor as well. I think they're M3 as well. You'll also notice on that 3D printed part there, if I just get my mouse over here, you can see there's like a little hole here and a little bit of a overhang. That's so that on the particular whiteboard that I have, it can perfectly be aligned to where the existing screw hole is that's screwing this into the wall. So I can basically just reuse that hole and attach this nice and securely there. And so that's the right hand side, simple as well. So we simply just screw the screws into the stepper motor and also into the driver board. Now the other thing we need to do is attach this driver board, oops, almost a meter across to the other side. So part of the reason why this will be a two-part video is I've got a whole bunch of cables here which are like a meter long, and you have to have 6 cables, 4 for the stepper motors and 2 for the ground and voltage. That back there. So I'm just going to fashion a little header pin thing using some crimping tools. So I'll show you that once that's been made up. So currently I've just got one side of the gondola working, and the gondola itself, this is version 1 of the gondola. I'm more than likely going to make another version of this that's a bit more dialed in. So for example, on this one, the timer cables come in flat, and it probably would make more sense for them to come in sort of perpendicular to that, sort of horizontal, vertical, simply because that's the way that they come off the rotor. So currently they've got a tiny twist in them as they go around the timer cog, which is kind of pointing out like that, and then they sort of have to twist to be horizontal. So I might change that. It's quite a small change, and it only takes about 2 hours to print this out. And then this version of the gondola, the stepper motor, is just zip tied on. It doesn't have to be that accurate for these kind of drawing robots. The servo motors are ridiculously accurate, and you'd be surprised how great the drawings will look from something that seems to have quite a lot of slop in the design. So you can simply just hot glue that down, or zip tie it, or we could engineer this so that it has a nice little screw in with all the right little lugs and everything, but it very much depends on what kind of stepper motor you're using. I think I've got 3 different types that I use. I use these DS929 ones that Pimoroni sell. These are quite premium. They've got the Metal Gear, so that's the DS929, if I can get that to focus in. And I also use the very cheap SG90. It'll cost about £1, so variance is there. And then the pen itself, so the marker pen, like I said, I'm using these Beryl ones. I usually use like a green or a blue pen, and these are just regular dry wipe. So just need to remember to put the lid back on when we're not using them, otherwise it'll dry out. So we can simply just pull the gondola away. And a lot of this is just gravity fed, so the gondola kind of keeps its position because we've got a couple of weights dangling from on the bottom of it. And similar with the timer cogs, where the cable sort of drips down the other side, we've just got some pegs on the other side of that to weigh that down as well. And as long as it's sort of under some kind of tension, the whole thing works fine. And there's an M3 screw that basically just screws against the pen to hold it in place, otherwise it sort of would retract up or down. So we just need that to sort of be have some kind of resistance there as well. So then we've got the timing belt. So this is the current design, and like I said, I might flip them sideways. So they go in and there's 2 screws which we can tighten against them, and it just holds them in place. They don't need to be that taut, to be honest, but by using this it works fine. Eventually, if you kept screwing and unscrewing them, they would come loose, I guess. So this is what the assembled piece looks like on the left side of the board. So you can see that we've attached the timing gear on top there. There's just 2 little Allen key grub screws that you get the Allen key with it. I bought a little kit from Amazon that had a whole bunch of these in. I think there's 5 in the little box. So I've got quite a few of these spare. So yeah, these simply just push into place. If you can see on the stepper motor, if I can get that to focus there, it has a flat top and a flat bottom, but it's kind of circular if you look at it as a cross section. And these have 2 little grub screws in, so you can put that in place, tighten it up, and then it'll stay nice and securely on there. And then the pulley simply just hangs over that. So whereas this is on the sort of corner of the board, the pulley will just sort of hang over there, and the weight will keep it in place. And when we issue command to rotate this left or right, it'll make the gondola lower or rise up. And also it can do that at angles as well, depending on what the other one is doing, because there's 2 of them. So it's quite an interesting mechanism and also quite simple. So attaching these to the board, we're simply going to hang them, one on the left side and one on the right side. The power is going to be on the left side, which is where the Raspberry Pi is, and then we've just got that cable that kind of goes across the top that connects the 2 together. And we're simply going to plug the Raspberry Pi in to provide the power to both of the servos. This actually seems to be fine, even though that you don't normally use a 5 volts on the Raspberry Pi to power servo motors. I found in practice it's fine to do that. And the gondola will simply just hang between both of them with weights attached. So attaching this to the actual the wall, so I'm in a wooden structure, so I'm simply using wood screws, and this just screws through the 3D printed part through the whiteboard. I think it's like a Nobo board, and mine is approximately 90 centimeters by 60 centimeters kind of drawing surface, so it might be a little bit more than that, edge to edge. But there you can simply see we just put in a screw and it's all in place, and it's been there and it's not fallen down, so I think I'm going to call that one a win. So wiring this one up, it does use a lot of pinouts. And this is because the driver board doesn't make this simpler. It's not like I2C, it simply just passes through the cables to the servo motors, or the stepper motors I should call them. So if I grab this one here, let me just take that off. So I've got one of these stepper motors here. It has this nice 5-pin cable on it, and the driver board simply has a matching connector, and it sort of holds it nicely in place there. We'll have a look at one of these in a demo very, very shortly. So what I've simply done is I've taken the 5 volts from the Raspberry Pi. One goes to one of the stepper motors, one goes to the other stepper motor. We also need to take a third 5 volt rail simply by just splicing together some of the cables for the servo that hangs off the gondola as well. And then we've got 4 cables that go to the left stepper motor, and then 4 cables that go to the right stepper motor to control the individual magnets on there. We'll have a look at that sequence. It's quite an interesting, you really get down to the mechanics of how these things work in this project, which is quite interesting. So yeah, we have got that 1 meter for cables. The only other thing I think to consider with the cables is the sort of size of the cables. So if we're running current through them, they probably need to be a little bit thicker than your regular kind of cable, just because they might overheat a little bit and get a bit hot. And then setting up the Raspberry Pi, so I would simply just download the Raspberry Pi imager from the Raspberry Pi website, flash an SD card, load whatever the latest version of Raspberry Pi OS is. So as we film this, we're on Bookworm, so I'd put the 64-bit version of Bookworm. If you're using the Raspberry Pi Zero 2W, that can take the 64-bit OS. I think the previous 2 versions only run 32-bit. It doesn't matter too much on the project we're doing, but the Raspberry Pi Connect, which is their remote control software, that works better on the 64-bit version I've found. So that's what I've got there. You can get the screen and the terminal up. And then we simply just want to connect this, kind of preload this when you use the Raspberry Pi imager with all the Wi-Fi settings for your particular location, just so you can connect to this. If you're using a different Raspberry Pi, one that has an Ethernet connector on it, you can just plug that straight in and away you go. But I will be accessing this remotely as I tweak the code and do kind of experiments on it, so it's great to be able to have access to this kind of live as you're experimenting with it. And yeah, I always do like a sudo apt-get update and sudo apt-get upgrade, or if you're being more modern, it's just sudo apt update, sudo apt upgrade, and that'll give you all the latest packages. So if you like what I do and you want to follow along with my videos, please give this video a like. Drop me a comment, let me know if you built any robots that draw things. I'm very interested in those at the moment. And if you've not subscribed to the channel, please subscribe. It means an awful lot to me. I put hours and hours and hours of effort into each one of these videos that you probably don't see behind the scenes. Lots of prep, experimenting, trying things out, making lots of mistakes, writing them up, and then document them on the website. So there's an entire course that goes with this video on Kev's Robots as well. We'll have a look at that towards the end of the video. I do go live every single Sunday at 7 o'clock British summertime we're currently in, and yeah, you can come and chat and hang out with me and discuss things at the end of the show. Cool. So let's have a look how this actually will work then. So this is the interesting bit. I saw a video on this and I thought, oh, I could definitely use that as my drawing robot. There's lots of other options I had to do this, to achieve the drawing a calendar on the whiteboard, and I thought this would be a great solution to that. So we've got our whiteboard, we want to be able to draw things on it, and we want to be able to program this plotter using X and Y coordinates. We want to be able to say, move the pen to this position, X and Y, and then draw a line, and then make the pen go up, and then we can form all kinds of pictures from that. But all we can do with our plotter is we can turn stepper motors left or right, forwards or backwards. That's all we've really got. So we need some way of converting stepper motor commands, like move so many steps to the left or so many steps to the right. We need to convert that into X and Y coordinates. And that looks like one of those head-scratching things, but it's a lot simpler than you would actually think. It's just a very simple piece of trigonometry can help us figure this out. So what we need is this function that will move the pen from one point to another, converting the X and Y into the number of steps for each of the motors to turn at the same time. You can see there we've got the origin point of our drawing space is going to be the top left of the drawing surface. The board I've got is 90 centimeters by 60 centimeters. That's what we're going to be using throughout this as our baseline. So the trigonometry, we can calculate the distance the left and right motors needs to travel. We convert the distance to steps using a steps to millimeters constant, and that'll be the same with both of these. Hopefully they'll be both very similar. If not, we can dial them in and make them just right. But we'll simply get this by a bit of experimentation. So we'll get the robot to draw a line on the board, and then we can measure that point. If we get it to do a really long line, that should give us even more accurate measurement of how many steps it's had to take to get to that distance. We can simply see this many steps took this amount of distance to draw. Once we've got that, we can put that into our code and kind of bake that in as a constant. And then to find out the length of C, so the way that this works, we are going to start our gondola at the very bottom middle of the board. So that in our case, if it's 90 centimeters long, the middle will be 45 centimeters, and it's going to be the very bottom of the board, so it's going to be 60 centimeters as the Y position. So our start is going to be 45 by 60. So we know the length of B, that's going to be 60. We know the length of A, that's going to be 45. And what we need to find is the length of C. And the reason we need to find that is because that's what we want to draw. We want to figure out what that distance is going to be. And as we move our pen round, essentially we use this same function over and over again. And if we know C, we know how many steps per millimeter. We can basically just convert that in a very, very simple formula to figure out what the distance of C is. So C, this is the very, very simple Pythagoras' theorem. C squared is equal to A squared plus B squared. Or another way of saying that is C equals the square root of A squared plus B squared. And if you want to write that in Python, it's simply just C equals math.square root, and then in brackets A star star, which means the square to the power of 2 plus B to the power of 2. So that will give us the distance of C. So very, very simple to work that out. And we need to find it for both of the motors, not just one. So we need to know how many steps to turn the left motor as well as the right motor. So you can see on this particular example here, if we're starting at 2652, we know what the distance between the middle and there is, so we know what we would have to travel to get there, and we will always start out from that same starting point. That's our code kind of depends on that. And then we can simply just convert each of those lengths for the left C, if you like, and the right C, and then we can figure out what the steps required is, and it's just the distance times the steps per millimetre. So looks quite complicated on the face of it, but you put this in a couple of functions and you've already got an X and Y position on your robot, and really that's all we need to do all kinds of clever stuff. We could even use other existing drawing libraries. We could take the brachiograph drawing library that we did the other week and make this draw those kind of brachiograph things. This is actually called a polar graph because it's got two stepper motors on it, and it kind of hangs down with gravity, just out of interest. So I thought I'd also talk about how stepper motors work, because like I said, on this particular project you actually get quite up and close with the mechanics of how this works in our code. So inside these 28 BYJ 48 stepper motors, there's a little gearbox. There's the spindle, which is how it kind of presents to the world, and inside there's a little DC motor. Well, it's not a DC motor in effect. It's actually a whole bunch, if you think about what's inside a DC motor, it's a whole bunch of magnets. And these are very carefully positioned, so there's 4 different phases or steps. And we can switch on using those 4 cables that are there. This is why it has these 4 LEDs on the driver board. We can individually switch on these motors and get it to sort of click round, 1 step at a time. There's 8 different sequences for those 4, and we can have a look why that is in the next slide. So we're going to have this starting position. We don't know where that will be. What we want to know is get to a good known position in our stepper motor. So we're going to put some power to the first magnet A, and it's going to sort of click round, and there's a whole bunch of other like magnets around the outer part of the stepper motor, and in the inside there's some kind of matching ones, and they're configured in such a way that they're slightly offset, and when you power one of the 4, it'll rotate to the nearest one. So that magnetic force will spin the spindle to the nearest position, so we get that first click, that first step. And then we can do step 2, turn magnet B on. The magnetic force will get it to rotate to the next position. Step 3, we get that extra position, and then step 4, that's the final one, and then we basically just do the whole thing again. Now, the way the mechanics, if you like, of this from a code point of view, we don't just switch on one magnet. We actually switch one magnet on, and then the next one, and then we turn that one off, and then we switch the next one on, and then we turn that one off, and then we switch the next one on. So it's kind of like a rolling on-off of the magnets. And you can see this in this little table here. And this table will appear exactly like this in our code, with 1s and 0s to represent turning on and off the stepper motors one sequence at a time to make the stepper motor turn round. It's quite magical when you see it working. And they're also very strong because of this, because they're almost directly being powered. You get this quite strong force, and there's a gearbox as well, which again just gives it even more torque where it presents to the real world. So yeah, each magnet needs to be energized, and then the next magnet needs to be energized, and then the previous one switched off, and we just keep going on and on. So if you look at this little truth table, this little diagram table on the right hand side here, we switch on A, we switch on A and B, or another way of looking at it is we leave A on, we switch on B, we switch off A, so just B's on, then we switch on C, and then we switch B off, and then we switch on D, and then we switch C off, and then we switch on A again, and then the whole sequence starts again. So this is like an infinite sequence. If we reverse that sequence, the motor will spin in the opposite direction. So we can actually just store these values in a list, and then just say list.reversed, which is quite a clever Python trick to basically get it to go in the opposite direction. Now, like I said, what's interesting about these motor driver boards is they've got these 4 LEDs on that represent those 4 different states of the motor, and we can see that table coming to life on these 4 LEDs. We'll have a demo of that very shortly, and you'll see that. So on this motor driver board, we've got the plus and minus on the right hand side there. It takes between 5 and 12 volts. We're just giving it 5 straight from the Raspberry Pi. And then we've got these in 1, in 2, in 3 and in 4, which is the inputs for each of those motor sequences, states. And then the code for this, we will run this code in a second so you can actually see this come to life, because it's a little bit small on the screen there, but I'll show you this in Thonny. But you can see the step sequence there. This is the exact sequence that we've just had on screen. In fact, I cut and paste this code onto that slide to show you this, and it's quite interesting to see how that works. And we simply just enable these one at a time, step through them, and then we do the reverse of that. So the step sequence, which is just that little list there of values. If you can see there, step sequence dot reverse is a nice Python thing. It basically just goes from the bottom up rather than from the top down. And then we're simply just going to count 512 steps in one direction, wait for a second, and then reverse that. So that's what the code will actually do. Very, very simple. And we'll run this on a Raspberry Pi Pico in Thonny in a second. In fact, let's do that now. So I'm just going to go over to Thonny, which I've got here, and I'm also going to get, let's see if I can get this on screen at the same time. So what I'll do, I'll show you the code kind of full screen, and then I'll show you it actually working at the same time. Well, actually, we can see it there on screen at the same time. It's as if I'd prepared for this. So there is the stepper motor. I've just put a piece of blue tack on there so you can see when it's actually turning round. So there's not too much to this. There's quite a bit of repetition because there's 4 different motors that we need, 4 different magnets that we need to switch on and off, and therefore each piece of code kind of gets replicated 4 times for each of the different magnets. So the first thing we do is from machine import pin, because we're going to be talking to pins directly on the Pico. We're going to import time. We're going to import sleep from the time library, because we're going to get this to go to sleep for fractions of a second. And I've got 3 different versions of the speed variable here. So 0.1 is like a tenth of a second, and then we've got like hundredths of thousandth of a second, and we can see how that affects the motor spin round. They basically just reducing the sleep time between each of these states. So we then define the GPIO pins that we're going to be using for the stepper motor. So I'm just using pins 0, 1, 2 and 3. I zoom back out a second. I'm actually using the Pimoroni Pico Explorer, which is quite a nice little project board. I think it's about $20 or something. So I've got a Raspberry Pi Pico W just there. I'm not using the breadboard, but I'm using the little pinouts that they've got there. So I'll zoom back in on that. Okay. And then what we then do is we initialize the pins. We need to tell MicroPython that these pins are output pins. We're going to be sending a voltage out. So coil A1, coil A2, coil B1, B2, and they're all basically pinned out, which just means this pins are outputs rather than inputs. Then we've got that sequence, that step sequence that we looked at on the board before. So that's exactly the same. I did literally cut and paste this onto the slide, so that should be identical to that. And this is going to energize each of those magnets in turn. So that's just a list there of values, a list of lists if you like. And then we have the set step. So we're going to take in 4 values, and then we're going to set the pins to be whatever those values are. So pin 1 will be W1, pin 2 will be W2, and so on. So a nice little helper function to do that very quickly. And then we've got this stepper test. So we're going to take in a delay, some kind of weighting value. We're going to take in a number of steps that we want this to rotate, and then there's even like a direction. Is it backwards or forwards? So if the direction is equal to -1, so that's reverse direction, then we do the step sequence, which is that little list there, dot reverse, which is quite neat. It means we don't have to do like a loop in the reverse order. And then we say for underscore in range. We don't even care about what that value is, that variable. We don't even give it a name. Normally you do like for I in range, but we don't need to use I, so we can do for underscore in range, and then the number of steps that have been passed in, and then for step in step sequence. So for each steps that there is in the step sequence, which is the 8, we then say set step and then star step. So we'll pass in what the value of that step is, and then we'll sleep for whatever the delay is of that. If the direction is -1, then the step sequence is reversed. So that looks like a bit of repetition there, because that's always going. Oh, it just says restore the original sequence, so it's undoing that. I see. So step sequence dot reverse actually reverses the order of the steps. I wouldn't have thought that. I would have guessed it would just, for that use, reverse it, but maybe not. And then we've got the main program, so we're going to say try except. So this is looking for any kind of keyboard interrupt. So if we press a key, it'll stop and then set all the steps back to 0, 0, 0, which will stop the step motor from turning. And we're going to say print rotating forward. We're going to pass in to the stepper test whatever the speed is that we set earlier up, and I think I've got that as a 1/10 of a second currently, so it'll be quite slow. We're going to do 512 steps, and the direction is going to be 1. We're going to sleep for a second, and then we're going to say rotating backwards, speed exactly the same, but the direction is -1, so it'll go in the opposite direction. And if we press a key on the keyboard, it'll gracefully stop the stepper motor, and it'll also switch off any power going to that stepper motor. And this just means if we're running this and we haven't got a main program, then just run the def main. We could actually get rid of def main and indent all that so it's always there, but this is what we've got. Right, so what I'll do now is I will run this. Let me just scroll up to the top there. So currently the speed is 0.1 of a second. So let's run this. So can you see the LEDs there? If I turn off the overhead light, you can see there, that's the sequence going ahead. You can almost see it looks like a Knight Rider scanner, the sequence of steps, and you can probably just about make out the blue tack is very, very slowly turning. It's almost imperceptible. So what we'll do is we will change this value to be, let's add a 0 in there, so it's 10 times faster. So I'm going to click run, and you can see now the lights are almost, you can't really see them, they're just flashing as a big mess, but you can see there the stepper motor is very slowly rotating round that, and that's 1/100th of a second wait in between. So let's add another 0, and let's run this again, and now you can see the stepper motor is really going at a bit of a pace, and you can see there the lights are almost constantly on, and you can see it's also saying that it's reverse rotating backwards, rotating forwards. So you can see there in the little console just down at the bottom of the screen there, rotating backwards. We could even put like a little status on there. Now there is actually a limit to how fast you can make this. If I drop another 0 in here and then try and run this, let's see what happens. It doesn't do anything, and that's because it's too fast for the stepper motors to actually get any energy in them. So it seems to be that that's the sweet spot. We can have it 1/1000th of a second. There we go. And they're quite powerful, these, even though this is just running off the Raspberry Pi. If I try to hold that, it will just rip my finger apart. So it's pretty neat that it can do that. So what we need to do is we need to have 2 of these in conjunction with each other, and when we work out what the distance we need the gondola to travel is, we basically just need to say to each of these, you need to turn like left one this many steps, and then the right one this many steps, and the gondola will move to the position. And one of the really clever things we can do as well is we can pass in to a function that will move the gondola. We can make it, if we pass in a sequence of these, that it will draw each one of the sequences and then lift the pen up, so we never actually have to say the pen up or pen down command. It can assume that when you pass it a coordinate, a sequence of them, that it will draw each of those in play. So we can use some clever code. We'll look at more of that drawing code next time, but this is something I thought would be fun to try out. Now these are quite cheap to buy, even with the stepper motor. I don't think I paid more than $10 for 5 of them, so put like $1 for one of these and $1 for the driver board as well, and it comes with all the cables sort of already with the connectors on there. They're like the JST type connectors on there, so quite like these. Not really used them before. They've got an unusual name to them, but yeah, pretty reliable. So yeah, that's the very, very simple code to make these spin round. It's like I said, interesting that you actually have to tell it each magnet to energize in a particular sequence. Normally with these things, you just have some kind of driver or some code, and you just say forward this many steps or back was that many steps. But on this one, you actually have to count the steps yourself, and you have to tell it which to energize in what sequence. And if you get it wrong, it doesn't move, it'll just jitter around, or just not work, or just get very hot, for example. So you do need to sort of watch your code with that. Cool. So if you want to get yourself one of these Kev's Robots maker hats, then go to kevsrobots.com/merch and you can pick one up for yourself. They're really nice quality and they're a bit of a conversation starter. I was in a restaurant in Italy once on holiday, and this woman on the table opposite kept looking at my hat every now and again. And then after we'd finished eating, she said, "Do you make robots?" And I was like, yeah. And she says, "So does my husband. He works for, is it Da Vinci, the company that has all the medical robots?" And he was working on that. And I was like, "I make toy robots. I teach people how to make smaller robots." But they were like really interested in what I was doing. I think I got 2 extra subscribers from that. So yeah, they're a bit of a talking point. So kevsrobots.com/merch to get yourself one of those. And if you want to join our Discord server as well, you can head over to kevsrobots.com/discord. It's completely free. If you click on the sign up and nothing comes through, just check your junk mail. It usually sends it to junk mail. I think that's because all email providers just look at Discord as being junk, which is a bit mean, but Discord's a pretty good community out there. I think it's been rated one of the best community environments that there are. And if you want to follow me on social media, then you can get some behind the scenes things. You can see how the robot itself is going. In fact, I'm just going to show you on this video here. If you can see just there, that's the gondola. You can just about make out the 2 cables as well, to ignore all the mess. But yeah, that's the thing I always look at, and I've still got the original subscriber count on the right hand side of the board there as well, which is oops, it's the wrong view, there we go. Which is what, when I started out YouTubing all that time ago, I think I've got 500 subscribers on the top of the page there. February 28th 2001 that would probably have been. There we go. So yeah, follow me on social media. So I'm on Threads at Kevin McAleer at threads.net. I'm on TikTok at Kevin McAleer6. On Instagram I'm at Kevin McAleer. On X I'm at KevsMac. And on Mastodon I'm at KevsMac at mastodon.social. And on Blue Sky I'm at kevsmac.bsky.social. Is there a particular social media platform that you prefer? I found Threads to be quite nice environment. It's almost like the new Twitter. I found, and big fan of Mastodon as well. I've got official Mastodon sticker here as well, so you can definitely go and check out Mastodon if you wish. I've got this one from Andy Piper, who's a Mastodon contributor as well. Cool. And if you want to join me, you can do this in a number of different ways. If you want to help support the channel, you can get your name in the end credits simply by going to kevsrobots.com/coffee, and it's basically the price of a coffee per video to get your name in there. So you can also do a super thanks and a super chat. Let me just make sure we've got those switched on now that the main part of the show is over. So a super thanks is the subscribe button gets replaced with I think it's a thanks button, and you can click on that and it's just like a one-off thing to say thank you for that. If you're watching this live, you can do a super chat and you'll get your name up in lights on there. Let's see, yep, there we go. And you can also join the Buy Me a Coffee membership as well, which is like a non-YouTube way of helping the channel. It's just the price of a coffee per month. So if you want to do that, you can get your name in the credits as well. There we go. So let me give a shout out to those people who've done exactly that. So we have Mary Louise Mayer has bought me a coffee. Thank you very much for that, Mary Louise. And Ian bought 2 coffees in the past month. And then on the Buy Me a Coffee membership side, which is, I'm looking over here, on this side here, we've got Shemi, we've got Alvaro, we've got Murray, we've got Jeff, we've got Steve, Dean Corty, Marlene, Brent and Tom. And on the membership side for YouTube, we have Orcsrad39, who's just resubscribed. We've got put my teeth in, Fafasin, we have Little Back Ford, we have Dale from Hybrid Robotics, we've got Paul, we've got Johnny, we've got Hans Van Chairlights, Stephen, Jonathan, John Paul, we've got Alistair, Cassie, we've got Tinkering Rocks, we've got Johnny Bates, Michael, and of course we have Tom as well. If you want to get your name in these credits, then you can go over to kevsrobots.com/coffee or kevsrobots.com/credits. I think it's the link for the same area, to be honest. So yes, you can do that and help support the show, and thank you so much to everybody who's done that already. So that's the main show coming to a conclusion. So if I go back to me here, so hopefully YouTube will be suggesting a video somewhere over here that it thinks you'll like from my repertoire of videos. I've got over about 300 and odd videos now on the channel. Each one of them is some aspect of robotics, Raspberry Pi, Python, and data science. There's all kinds of stuff in there, home automation as well. So definitely check one of those out as well. And it's at this point in the video I'll say thank you so much for watching, and I shall see you next time.